Yeah, thank you.
So thank you very much, Jalal. It's a pleasure for me to be here, and thank you for the nice introduction. And it was a real pleasure to work with you some time ago. So anyway, what I'm going to do today is basically focus on a tutorial view. So I'm going to say things very basic. So if you're an expert on robust optimization, then probably you will not learn anything, because that was the idea, that we thought it was a good idea to do an overview. But anyway, I will try to emphasize important issues that sometimes if you focus pretty much in a particular problem, you may forget those kind of basic things. So we have to have global overview of what is going on all the time, and this is a critical point. So what I'm going to do today is basically review different, well, the material of you now is over here. You have all the material there. Today, I will review robust optimization. The first thing that I will do is to introduce the basic concept. The second hour, part of the second hour, we will focus on the basic algorithms to solve those problems. There's a basic algorithm that almost everyone uses. And then I will use very stylized, simplified models that we can use in Power System. I will do an overview of medium-term planning problem and long-term planning problem. Again, my idea is to have an overview, to go to the critical point, to the why robust optimization is relevant in this particular context, not to analyze a particular problem with very, very much detail. So I will not be very precise in terms of what I say in terms of Power System in that sense. But if you want, you're welcome to ask me anytime. We can go into the details of some of the problem. I have some experience applying robust optimization to a number of Power System problems, not all of them. But then we can discuss particular details on implementation, right? So that's so the material is there, and then for this initial hour, I'm gonna first of all describe what we can call single-stage robust optimization, of just robust optimization by itself. Then the more interesting one, which is the adaptive robust optimization. Then something kind of a strange thing, which only few people have been looking at that I think is particularly interested, in which we distinguish between different type of uncertainty. So not all type of uncertainty is the same, so if we treat all the uncertainty in the same way, maybe we are not doing the right thing, okay? So we will look at this multi-scale sometime that we call in this particular case adaptive robust stochastic optimization. And then I will say probably Jalal knows more than me about distributional robust optimization, which is a way to describe actually the robust set, the set in which we describe the uncertainty in a sophisticated way. It has been a lot of mathematicians has been focusing on this kind of approach. I think my particular view is just an extension of the more classical adaptive robust optimization, more classical description of the robust set. But anyway, I will say a little bit about robust set and the uncertainty budget. This is the way we control the level of security, the level of how secure we want a solution to be. With respect to, typically we have a trade-off between security and cost. So if we want things to be very, very secure, we spend a lot of money for that. For instance, I guess you use a bicycle to come here every day, and you may say, well, I have to get there no matter what, so I should buy a second bicycle because there is a non-negligible probability that my first bicycle is broken. And you can say, well, but if I have two bicycles, still I have the probability not negligible to have the two bicycles out of order, so I should buy a third bicycle and use to keep buying bicycles and you get bankrupt, right? So this is what we do with robust optimization in that sense, which is the trade-off. How many bicycles should you buy, depending on how important it is for you to be here no matter what. So this is basically the trade-off that we organize. We can do that using uncertainty budgets in this particular case. And then we will a little bit mention why we use robust optimization as well in that sense. Okay? So again, I'm very tutorial here, so if you know a lot about that, I don't think that's the thing. So single-stage robust optimization is just robust optimization. The type of problem that we have in this case look like that, right? So in this case, we have a preventive view, okay? So we are over here. We want to make decisions in this variable x that belong to a particular set x. We want to make those decisions in such a way that we anticipate whatever happened over here with the uncertainty. So U is a variable. We use variables to describe uncertainty, which is a weird thing to do. Uncertainty, we usually use parameters. A random variable from the optimization point of view is a parameter. It's not a variable. A variable is what we decide. We don't decide on the uncertainty. So over here, we are using variables to describe the uncertainty. In this particular case, we say the uncertainty, whatever it is, belongs to this set that we call the robust set, right? And we want to make decision over here in such a way that the worst, because this is max, we want to minimize whatever this is. We want to minimize that, and we want to select this variable describing uncertainty in such a way that it happened the worst. So if this is a hurricane, I'm planning the power system of this island in which we are, and I want to plan the system in the best possible way to reinforce lines, to actually install local generators, whatever. We want to reinforce everything to get ready for the hurricane. And this is a hurricane that may destroy, well, fortunately not here, but in some places may destroy, let's say, half of the system. So this is what we are doing here. And we don't have the option to react later on, which is not the case of a hurricane. If we plan, we duplicate, we install extra equipment, and then the hurricane happens, then typically we have an extra step, which is we actually, after the hurricane, react the operator, try to operate the system in the best possible way. But we will look at that later on. So, but this is the kind of thing that we are doing in the preventive manner. So we want to do things, buying bicycles, or maybe reinforce the power system in this island in such a way that when something happens and we want to see that this something to be the worst possible thing that may happen, we are ready for that. This is a preventive view, right? This is a basic concept in this kind of problem as well, right? Okay, so, and then let me say in this particular case, what happened as well is that we don't have recourse that we call. We don't have the possibility of reacting once the uncertainty materializes in the worst possible way, okay? So that's the framework that we are using. Is this, someone can tell me an example of these kind of things? That you get ready for something that may surprise you, a hurricane, but then you don't have option to react. Any example of this type? I'm a friendly person, so please, you can ask whatever you want. Well, market work like that, and I'm sure that you're close to Jalal, you know a lot about market. You go to the market, you offer, and that's it. And then whatever is happening in the market, you get a price, and you get whatever it is, and that's it. You don't have option in this particular market. You may have a collection of markets, one after the other. But just look at the given market. You have the option to offer in the market, and then prices materialize. You don't know the prices. It's a random variable in this case, well, to some extent, okay? And then it's something for you, from your point of view, something that you don't know, and you have to offer in such a way, taking into account that prices may be one type of other type. And then you don't have any option. The market clear, you get a price, and you get paid out of that, and that's it. Okay? We may model a multi-market system, but this is not what we are doing here, right? And maybe in a multi-market system, you may have limited options to alter what you are doing as well, okay? So this is one of the typical examples. We may have other examples. I don't think this is that common, but anyway, it's the starting of the robust optimization. In '72, I believe, a gentleman in the Boston area, not in MIT, but in a not well-known university, Northeastern University, invented this technique and formulated this problem and published this problem in Operation Research, in the journal Operation Research in the early 70s. Nobody looked at that and said, "Boof, it doesn't matter, nobody cared about these kind of things." And then it was in the late 90s that Dimitris Bersimas at MIT said, "Well, this is a good idea," and reinvented the whole idea and make it the whole things very well known to everyone. So that's the history over here. Soyster was the gentleman that produced the first idea of robust optimization. Okay, so so this is the type of problem. So let's do a very simple example again. Let's do this example. So we are just operating in a market, and for some reason, for whatever it is, I'm using discrete variables in this case because it's the only way to solve those problems. We will see that these variables are not discrete. Then we get into trouble. We need to use the algorithms that we will use in the second part of this class to describe. But the algorithm is kind of involved. So if we want to get the sense, let's do things simple, understand the concept, see which are the type of result that we get out of that, and then when we comprehend that, then we can build an algorithm. Because at the end of the day, if you have a huge problem and this problem is the same thing, okay? Just a computer in between, okay? But conceptually, if you can formulate that, you can formulate the huge problem. There's no difference, okay? So that's the problem. So my advice to all my students at the very beginning is that you should do things very simple, understand fully what is going on in all the details, and then you can produce something which is sufficiently complicated in such a way that the actual outcomes are not evident, they are not clear. You cannot connect the input to the output in a clear way. Okay. So this is the problem that we have over here. Let's say that we are offering a market, and we have the options. This is the variable, the quantity that we are offering. It can be 3 or 10. Nothing else, either 3 or 10. Why? Well, can be typically it's a continuous thing between my minimum power output and my maximum power output, even though, but anyway, just for simplicity. And then let's say that this is the price in the market. Okay, the price in the market is 4 or 7. Nothing else. Again, because of simplicity. Okay, and what I want is to maximize my profit, and I want to do that. Well. This is the problem, just as an example. You may not want to do that in real world. Again, I'm doing things which might not be realistic. I'm just focusing here on the, let's say, operation research component of the problem, right? To clarify the concept of the idea. By the way, operation research was created to solve real problems. Some of you, I guess, are interested in not just in electricity market, but or in power system, but on the math behind that in operation research. And operation research, even though we have now a lot of mathematicians doing operation research and doing beautiful algorithms, operation research was actually created to solve real problems, and actually in the Second World War to actually move facilities and troops and everything around. So it was actually built to solve a real problem, as opposed to build beautiful algorithms and then eventually apply those algorithms to something. So I believe, at least my view, is that we should try to look at real problem, and then if we get problems which are so complicated that the algorithms that the mathematician has produced are useless, then we will produce new algorithms or new ideas. So try at least to enlarge and to develop the algorithms. That's my view. Anyway, that's the problem in this case. So we want to offer either 3 or 10. The price is going to be 4 or 7, because this is just an example. And my profit will be the quantity that I'm offering times the price will be 4 or 7 over here minus my production cost. 5 is my production cost. And I don't have constraints. I'm free of constraint. Of course, this is a very simplified model, but we can. This is, I don't have any option later on. It's a market I offer. The price materialize, I get paid, this kind of thing, and that's it. Okay? So this is a single stage. We call this a single stage robust optimization. And I wanted to formulate robust in this sense. Okay? So I want to pick up to actually put myself in the worst condition. Okay? If the price is 7, I will be happy. But if the price is 4, and this is the condition that I want to identify. In this case, it's pretty obvious that the worst condition, the worst situation is price 4, because I'm trying to maximize my profit. But in reality, this might not be trivial or optimal. We're doing things trivial here, but in the sense, you're going to describe a bunch of prices, maybe 24 hours, all of them interconnected, because price in 1 hour depends on the price in next hour. And then your production might be, your offering here might be actually conditioned by the facility that you are using here. Maybe this is a wind power plant, it depends. Again, it's random to some extent, and we have to model that somehow. If this is combined cycle gas turbine, then you have a minimum and maximum between. So we may have constraints related with the past, with the future. This is a single period. We can produce heats multiple periods, but at the end of the day, we are doing the same thing all the time. Okay, so this is the problem. So I want to find out, in this case, pre-obvious is 4, but I don't know. I want to find out which is the best way I should offer in such a way that for the worst realization of the uncertainty, I'm good. In that sense, I'm protected. So this is the kind of decision that we can make, okay? In this particular case, we can solve this problem in since this is a discrete, we can actually solve the problem. So we have two options. If we decided to offer 3, the problem is like that. And then the solution will be -3 if the price that realized is 4. We get the minimum for 4, and it's -3. But if we offer 10, okay, which is this case, then the price is going to be over here 4 of 7. Again, we get the price 4, which is the lowest one, and then -10. So we have on one hand -3, on the second hand -10. And since we want to minimize, we want to maximize the profit, we pick up the -3. So that's the thing. If you formulate those problems, a huge problem, multi-period, a lot of constraints over here, a lot of constraints over there, at the end of the day, you are not doing something much different than that, okay? So please make sure that you understand this, and then when you fully comprehend this, you move to the other thing. Because getting a mess of computational stuff is not good for your mind to function, okay? So don't get stuck in computational issues before you get a fully clear view of what is going on in the problem, okay? So one interesting observation here, these problems, I believe they don't have many applications in reality, but they have an interesting property. Originally, the deterministic problem, the problem with this over here, without the intermediate stuff over here, if it is a linear problem, of a nonlinear problem, of a mixed interlinear problem, the robust counterpart, this single stage robust counterpart is the same type of problem. So if we have initially a linear programming problem, the robust version is linear as well. That means that we are not introducing this complication of the uncertainty in the robust sense. We are not actually complicated the structure of the problem. We are not producing a problem which is essentially more complicated, okay? This Professor Bersimas has a very beautiful proof of these kind of things in his many papers. Okay, so let's move to a little bit more interesting model framework that you may be interested in. Any question is welcome at any time. Okay, in this second framework, we call adaptive robust optimization because we adapt. So we have 3 steps here. We plan for whatever it is, for the good. The uncertainty realized for the bad against us, so to speak, and then we react in the best possible way to try to fix the trouble produced by uncertainty, okay? For instance, a hurricane, we planned the Zealand area against hurricanes. Well, no hurricanes here, maybe a major storm that may disrupt in a very significant way the system. And then we have a clever, interesting, competent, ready, and efficient operator that does whatever has to be done to try to minimize the impact of the storm, right? That's the framework that we're using here. This is applied to many other things, natural disaster, and I have described. Also, not really bad things, your bicycle. You plan how many bicycles you should have in such a way that every morning when you realize, you look at your bicycle is okay or not, and then you can come here. If you don't get the bicycle, then you can do something else. You borrow a bicycle from your neighbor or whatever. So this is a natural way to do things. Plan whatever bad happen, and then you react to try to mitigate this fact, okay? This is what this has to do with adaptive robust optimization, okay? That's the natural framework. And it's fit to many things, and particularly fit to important decisions because, well, we can use that for not that important decisions, but typically important decisions like buying a new bicycle or building a new transmission line, they are costly. So you want to make sure that you are doing that very carefully. So in that sense, I think this is a very natural way to look at the problem. So anyway, that's the structure again. And let's look a little bit. We have a first level over here that represents the planning strategy prior to the uncertainty realization. So this is the uncertainty realization. Typically, my planning decisions do not depend on the uncertainty realization. So if I decided to build an extra transmission line connecting, let's say, the peninsula with Norway, which is a good thing to do for many reasons. And maybe I decided to build a new line over there, or I may decided to do whatever other thing. The decision of building a transmission line, the decision of building a generator has little to do with the actual uncertainty realization. It's driven by that. So if the demand grows, I will build a particular line. This is the driver for that. But my decision of building one line of another is not typically related with the uncertainty. So this X does not depend on this U, because there are different things in general. Well, we may have exotic problems in which this does not happen, but my decision of building whatever I decide to build to enhance this particular power system of a particular area is driven by, but is not related to the actual realization of the uncertainty, okay? But over here, so this is the first stage, which is the planning stage. Basically here, what we will do is, should we build an extra transmission line? Should we build local generator in different towns? Should we connect this part of the system with another part of the system through lines, or maybe a DC link? Should we actually build batteries somewhere else? All these kind of things are the planning decision that we decide over here. The uncertainty, whatever the uncertainty we are describing, typically in a power system, we have, let's say, the big uncertainty, the long-term uncertainty, we will discuss a little bit more later on that. But this is basically the increase in demand, okay? The increase of the peak demand. But by the way, the peak demand today and the peak demand in this island, if you want, the peak demand today and the peak demand tomorrow is the same. So if our window is one day, the peak demand is not stochastic, it's deterministic. It doesn't change. In one day, the peak demand, because you have to install more power, you have to install more demand. And so the maximum possible demand that we can extract from the system from one day to the next day is not random, it's stable, okay? And well, let me discuss this a little bit, but we will discuss later on. And if the window that we use to look at the uncertainty of the uncertain phenomenon that we are describing is 1 year, during 1 year, the wind production in Denmark is basically the same. The quantity of wind power produced in 1 year and the next year, if you do not install more wind turbines, is the same. Unless we have a major climate change issue that we'll not consider over here, because that will allow us to go a more complicated thing. So if the window that you have in 1 year, wind is not random. The amount of wind that you have in a particular year is basically the same. Even the correlation with the demand is basically the same. If you look at those data and you analyze a little bit the statistics, what's going on. So it's important, something which is the stochasticity of a particular parameter, it depends on the time window that you are looking at that, okay? You have to actually change the mountains of this country. Well, there's no mountains here, right? You have to change the geometry, the geography, okay? To actually change the wind regime. So of course, from one day to the next day, the wind may change dramatically. So in one day to next day, the wind is very random. In 1 year, it's not random. So if we are doing planning studies, and for planning study, we are looking 20 years in the past, and we are looking 20 years, and the demand is going to grow. This demand over here is going to grow. We're going to look what is happening in 20 years, and then we are planning. We are enlarging the system for meeting this demand in 20 years in the future. Then for that purpose, the wind is stable, unless you build more wind plants, but this is something else, okay? But the actual wind condition, operating condition. So that's important. What I'm saying here is that uncertainty is something that you have to look carefully. So say all the uncertainty is the same, and I use the same thing for all the uncertainty, and I model all the uncertainty the same way. Well, I don't think this is a good idea. You have probably 90% of the papers in the literature actually do that. But this is not, I think we can do better than that. That's the point, okay? So anyway, the first level that we have over here is the planning, okay? Second level is the uncertainty realization. We are using here, again, a variable within a set. We will describe later on a little bit more about this set, okay? Again, the uncertainty, or the description of the uncertainty depends on itself. It typically do not depend on my decisions. So the wind availability, I may decide to build wind power plant or not to build them in a particular location, but the actual wind resource in this particular location does not depend on my actions with respect to that, okay? But when we go later on to the third level, which is over here, the third level represents the operating actions. Once that uncertainty has materialized in the worst possible way that we are doing, okay? Then basically we will react. And then in the third problem, in the third level, the y, which is the variable of this problem, it depends on everything. So it may depend on the actual realization of the wind, and it depends on the actual investment. So if we build plants, so we will have those plants available over here. And of course, the realization of the uncertainty will affect the way we operate the system, okay? So that's the framework that we are developing here, okay? Okay? So observation here, which is important, I believe, is that we have here two types of protections. We have preventive protections. So we are doing things before the fact to make sure that things develop in the way that we want. So it's the planning stage. This is preventive type of thing, or ex ante, we call sometimes ex ante protection. We are doing things, we are investing, we are reinforcing the system in such a way that we get protected against the actual realization of the uncertainty. And then after the fact, we have corrective protection, because we have possibility to react. This is what we call recourse. In the more traditional stochastic programming framework, we can react with respect to what happened in the state of the uncertainty, and also to correct the situation, okay? So the adaptive part came over here. We are adapting to the actual realization of the uncertainty once we have actually making decision to protect the system in the best possible way, okay? Okay. Okay, let's do a little bit more in detail in this case. So we can look at power system planning, long-term planning problems. We want to, for instance, reinforce or expand the transmission network. So we will have many options for expanding the transmission network that we describe with this variable x. Typically, they are binary variables. Either I build this particular transmission line or not. So we have a bunch of variables here. Many of them are binary, and a number of constraints, budget constraints. I have a limited amount of money. I cannot build as many lines as I want. So which is the critical lines that I want? I may have intertemporal constraint over here telling me that I have to build that line prior to build another one over there. And so we may have a very sophisticated description of the planning problem here. All these are basically, but we will have mostly bounds of this type that limit our ability to expand the system, either technically or economically. So those are technical bounds describing the actual functioning of the different components of the system, right? And they were also, they might be also bounds related to the budget that we have available. This is the uncertainty that we will describe later on more in detail. Uncertainty that realize not connected directly to this problem. And then we have the reaction. In this particular case, we are describing the expansion of the transmission system of a particular power system. This may be a bunch of unit commitment problems. So this is the operational problem describing the actual operation of the system. So we are actually planning the system for 20 years. In principle, we have to describe what is going on in the 20 years into the future, right? 20 years times 365 days, okay? So we have what we should do, okay? Because we make the planning decision taking into account the whole future. Maybe we actually build here a unit commitment for 365 times 20, we may get an unfeasible problem. But anyway, when I was coming here yesterday, I was actually reviewing a very interesting paper of chemical engineering people that actually they produce very sophisticated mathematics for optimization for a number of reasons, and they were solving problems with quadrillions, that this is 10 to the 10. So they were using 10 to the 10 variable, 10 to the 10 constraint of this type of problem with no much problem. If you use a particularly careful decomposition technique, we can do that, okay? So 10 to the 10 variables, 10 to the 10 constraint, this is a kind of problem that we can easily get if we are in the power system in long-term planning problem of this type. So this is the kind of thing that we want to do. Okay, so of course, alternatively, we can produce a very reduced, compact, simplified version of this many unit commitment problem that we have to do. But anyway, that's the choice that we have to select in a particular setting of condition. So let's do an example in this particular case. Let me go a little bit further. So we have over here a generator, which is a very expensive one. The cost is 10, okay? And we want to supply this demand. We use this generator with cost 10 to supply this demand. And then we have, well, this might be the peninsula here in Denmark, and this might be Norway. So we have much cheaper power over there because of the wind stuff. Sorry, because of the water system. So anyway, whatever, I don't know, probably this is not expensive here either. Anyway, we have an area over here with expensive generation, and we are using this expensive generation to supply demand in this particular area. But we have the option to connect these two areas with a transmission line to another area in which the cost is pretty small, okay? This is what we want to do, and we are going to build a very simple problem. So in this case, we are going to say that the demand over here is going to be just 3 or 5, okay? This is 3 or 5. The cost of this is 10. The cost of this is 5. And we are going to build only 2 alternatives to building this transmission line. Okay, so the transmission line that we are going to build here is going to be just two options, which is 2 or 4. Okay, so let's look at, we have already the problem over here. Look at this problem. So I want to minimize the whole operation of the system planning and operation cost. Okay, the planning cost is over here. I can build this transmission line, which is either 2 or 4. So we can transfer 2 or 4 over here using a very simplistic description of a transmission line. I'm sure that we can do better than that, but just I'm going to the concept here. So this line can be 4 or 2, okay? And then I know that the demand is over here, is my uncertain variable in this case. This can be either 3 or 5, only 3 or 5. In reality, I have a multiplicity of things, 20 years, and I have to describe the 20 years within a framework similar to that one, is what we have to do at the end of the day. Or maybe I can compact the 20 years somehow, but that's the way I want to do it. And then I operate the system. Once I know which is the size of this line, I can operate this generator, which is the cheap one, and this one, which is the expensive one, to supply the demand. Okay. So we want to find out if either I built this line to be 4 or to be 2. The demand, I don't know what it's going to be. It's going to be 3 or 5, but I want to pick up the demand level, which is the worst for me. Okay, that's the way robust optimization works. Okay, and then I have these 2 operation variables. This is the production of this machine. Y2 is the production of machine 2. Y1 is the production of machine 1. Okay, so the cost is going to be building the actual line. The building cost of the line is 1 times the actual size of the line that I build, either 2 or 4. Okay, this x will be 2 or 4. Over here is a variable. It's our planning variable. Then I have 2 operating variables. Operating with this machine costs 5. Operating with this machine costs 10. Okay, of course the numbers doesn't make sense. This one, as compared with this 5, whatever, they're just numbers for this to function. They are not realistic. And then I have to supply the demand, which is 3 or 5. This is the driver for my investment in the line. Okay, because the demand over here is going to be whatever it is. I want to make the trade-off between keeping using this expensive generator or using this cheap generator through the line. Okay, so the production of this machine, but the production of this machine, both of them together should be the demand that we have over here, and the production of this machine, Y1 should go through the line, so it should be below the capacity of the line. And I built either 2 or 4. Okay? So very simple kind of thing, very simple kind of thing, but not very different that if you want to do a transmission expansion planning problem, it's not very different than that. At the end of the day, you will produce a more complicated formulation, but conceptually it's not different than that. So my advice, my observation, strong advice is be very familiar with this kind of thing. Feel it, not just not understanding. To understand things is simple. To feel them is a little bit more complicated. You have to go over that, okay? So that's the problem that we want to solve. And in this particular case, it's obvious what is going to happen here. Not sure if it is obvious what is going to happen here, but okay. So since it's very simple, we can easily solve it. So again, we do the solution. Let's spend some time looking at the solution. Actually, we start with x equal 2, which is over here, and then I solve this problem. And for this problem, I have 2 options, 3 and 5. So I select 3 and I select 5. In the solution is 22 in one case and 42 in one case. Since I want to select the demand in such a way that this is the worst, not the best, the worst, instead the maximum, so I'm going to select this one. Okay? And this is what I do. We select the worst one, and then we have the other option, which is 4. This 4 over here, and then I have again 2 options for the demand 3 and 5. So I do the 3, and then I do the 5, and in this case the worst is this one, is the 534. But now, so the worst is 34 in this case, but we want to select, now we are back over here for the whole problem, which are the two options. The second worst was 35, the first worst was 42. So we get this 35, this 34, which is minimum in that sense, okay? And so this is what we do, which means we built actually, the option 4. We built the big line to basically be able to take advantage of using the chip generator. It's over here. So we built this big line, this 4. We built the big line to be able to use this chip generator. Pretty obvious in this case. Probably you look at the problem and say, okay, so you did a lot of stuff here for nothing. That's okay. But in reality, things are as simple as that. And you should be able to throw a huge problem with a quadrillions variables and quadrillion constraints. You should be able to identify this behavior. If you cannot do that, you're not filling the problem, you may not be getting the right answer of the right solution to the problem. Okay. Okay. So some observations related to this problem. Those are complicated problems to solve. In general, we need specialized algorithms to do that. Those algorithms, we will spend some time looking at the structure of those algorithms. Maybe some of you are very familiar with them, but again, we are doing here a tutorial, so hopefully some of you are not familiar with them. Basically, what we do is find a way to merge these two problems. This requires some nice properties of the third level problem. We call this the third level problem because level 1, level 2, level 3. So the level 3 problem, it has nice property. For instance, if it is linear, we can do nice things out of that. If this problem is convex, an interesting class of convex problems are the second order conic programming problems. So we can use some properties of this problem to merge these two together. And then typically we end up producing a problem which is, this is max-min. We produce a problem which is just max. And then we have a problem which is min-max. It's a two-level problem. And for that, we typically use a decomposition technique that is called column and constraint generation. And we will see that we will look at that and we will say, gee, this doesn't make sense. This is crazy. Why you want to do that? This doesn't make sense. This is, if you look at that, you have some mathematical feeling, this is what you will say, okay? But curiously against the intuition, it worked very nicely, okay? And we will see what it is. Okay, so, okay, let's look another further step over here to clarify things, and another structure of another model that we call adaptive robust stochastic optimization. Unless you have any question. Yes?
So for solving the robust optimization problem, we always go for the worst case scenario, right?
Well, we have, let me say yes or not, if you allow me. We will have here, I haven't spent significant time yet to look into the robust set. So I'm saying the demand is going to be between 3 and 5. I can say many other things. And I can produce a very sophisticated description of this set. And we will spend some time on that. So let's say that you have mechanisms to control the level of robustness that you want to impose on this set. And we will look at that thing, again, introductory way. We can do more general things. But anyway, you want to do things the worst from this point of view, but limited, because you can actually describe this setting up particular way in such a way that you limit with these works it is. Because, I mean, the worst, if we are modeling hurricanes, is that the hurricane came and there's no system, no more system. Okay? The whole system goes away, so you have nothing to do. So you can say the hurricane is powerful in such a way that can take away, let's say, 10% of the system. And then we want to find out which is the worst 10% of the system. This is what we say. And inside this set, we are going to say that. We'll say, take away 10% of the system, not the whole system. The worst thing will say the whole system, but then we don't have any problem. This is the kind of things that we are going to say. And we know that we want to take away the 10%, but which is the worst 10%? This might not be trivial to find out. So you need to solve the problem to find out. Okay?
And what if you have more than one uncertain variable?
Well, they go all together. We will have some example of that, but no problem. I mean, you have a set for the demand, another set for the other. In this particular case, let's say that the investment cost is 1, and say the investment cost of this is 1. So let's say that this is not 1. It's whatever it is. So I can describe the investment cost over here and a random variable. This guy is going to build a combined cycle gas turbine, if it's going to be, but I don't know what is going to be at the time of building them. I don't know which is the. So I will have another random variable for these things. In this case, the problem becomes a little bit more complicated because we have a product here. So I need a variable for the cost, another variable for the actual, what we built. So I get things complicated. Did this happen? But again, this operating cost, 5 or 10, can be random as well. I don't know which is the operating cost of this machine, because this is going to be 20 years into the future, so which is the operating cost? Again, I can produce, these 5 or 10 can be random variables as well. No problem. Well, this is a problem because it's bilinear terms. If we have product to variables, we call that bilinear terms, and basically, if this happens, bad. Bad. Okay? So we have, at least we have to do complicated things. Yes?
I'm just curious about distribution. I mean, of course, if the problem is not so clear, you cannot go like picking up 1 second. And you said that it's possible to merge. Could you elaborate more on this example, how to merge it using strong?
Well, in this case, well, yeah, we will do that carefully later on, but yeah, we can solve this is a linear programming problem, right? The variables of this problem as y1 and y2, so this is linear in y1 and y2. This is a constant, so we can write the dual of this problem. And the dual of this problem is a max problem, right? So this is a max problem. The dual of this problem is a max problem, so a max-max problem emerges naturally. You can write just a max and merge together all the variables, the dual variable of this problem, and the d, because the d is the variable of this problem. So we will have a problem which is, we have just 2 constraints. So we have 2 dual variables, lambda, let's say lambda 1, lambda 2, and this variable d. So the merge problem will be, the variable will be d, lambda 1, and lambda 2. We will do that a little bit more carefully, yeah. But this is one thing that we can do. We can do other things as well. But this is typically the best thing. Other thing that we can do is just say, well, this problem is a linear programming problem, so I can write the optimality condition of this problem. KKT condition, well, since it's linear, it's generally better to write primal constraint, dual constraint, and a strong duality equality. We can write that, and take this as constraint and put it together to this problem, This is generally not a good idea. I was promoting this kind of doing things some very long time ago, but in this context, it's not generally a good idea, because KKT conditions are terrible conditions. They are nasty. KKT conditions are non-regular. That's the basic problem. So they don't comply with the regularity conditions, which means that any optimal solution, the gradients of the active constraint and the objective function are not linearly independent, and that has many terrible consequences from the optimization point of view. So basically is the, well, you can, let's say, this kind of theoretical argument, but nonlinear constraints, they are perpendicular constraints that tell you either this is 0 or this is 0. okay? Because the product has to be 0. This is bad, because you are jumping from one place to the other, okay? Either is one is 0 or the other is 0. So it means that one of the two variables, one has to be non-negative and the other 0. And this is jumping from one axis to another axis. Let's say that you have okay. Okay, this looks good. So let's say that this is x and this is lambda. So you have a constraint which is x lambda equals 0. And then if you want lambda non-negative and x non-negative, this is a typical, very simple structure of, that means that either you are here or you are here. So your algorithm is going to jump back and forth, and that's terrible from the computer science point of view. From the algorithmic point of view, it's bad. So we can look at that in many different ways, but at the end of the day, it's great numerical trouble. And we can try to escape this numerical trouble. We can try to be clever. We can do many things, but at the end of the day, it's better to get, if you have the option not to do that, don't do it, okay? And in some cases, we have the option. That's the only point. Okay. Okay. Okay, so let's go a little bit to this adaptive robust stochastic optimization, which will move us, if I have a better looking, that one. So over here, let me further elaborate a little bit about what I mentioned previously. So we have here two types of uncertainty. I'm distinguishing here two types of uncertainty that we already described. Okay, this is my building decision and building transmission lines, for instance. Okay, this is the realization of the uncertainty is the first uncertainty. This is the uncertainty related with the peak demand. I'm looking 20 years in the future, and I don't know what is going to be the peak demand in 20 years. I know it's going to be bigger, hopefully, because otherwise the economy will be down. So let's say that the economy is going good. We are improving, and eventually the demand is going to grow. We are going to describe here the peak demand, okay, with this uncertainty. So I want to be protected to the peak demand. So I want to have enough capacity, enough transmission line, of enough generation capacity to be able to supply the demand. This is the driver for this, okay? But in a particular day, the demand is not, the peak demand is not going to happen. It's going to happen something else, something below the peak demand, okay? If, depending on the weather conditions, maybe we don't have to use heating system, we don't have to use air conditioning, whatever it is. So the realization of the peak demand in the different nodes of the system, it depends on many conditions. And this is something that is depending on day to day. So the peak demand over here is not going to change from today, from now to tomorrow. But the actual realization of the demand, if whatever weather conditions change dramatically, probably we are going to change in a very significant, let's say that suddenly temperature drop to -0 tomorrow. And so everybody will be starting the heating system, and then the demand, I guess, a significant part of the heating system over here is electrical, so the demand will grow very significant way. And 1 week after, this doesn't happen, so beautiful weather like today, so the demand is going to be down significantly. So anyway, the same thing with the wind on the solar. Tomorrow we may have a very windy day. The day after tomorrow, maybe no wind at all, okay? So this is what we call the short-term uncertainty. So once we know, let's say in 20 years from now, that the peak demand is going to be 100, along the days of this particular years, 20 years from now, okay, the demand is not going to be at maximum all the time. It's going to be changing all the time. Okay, and the same thing with the wind. The wind, day after day, is going to be changing all the time. And this is the uncertainty that we are describing here in a stochastic function. Okay, so because they are very different type of uncertainty, and I don't think it's a good idea to actually merge together all the uncertainties over here that you may do that in some cases. So over here we are saying we want to be robust with respect to the long-term uncertainty, so to speak. I want to be robust to be able to meet the demand, to have enough capacity to meet the demand in 20 years, assuming whatever I assume with respect to the growth of the demand from now to 20 years, okay? But then, for the actual operation of the system, to describe the operation of the system, I want to describe the operation of the system for the many possible realization of the day after day uncertainty, which is what happened with the wind, what happened with the solar, what happened with the actual demand, okay? So some people call this multi-scale uncertainty, because we have different scale in the uncertainty, right? I prefer to call it short-term, long-term, but it's multi-scale uncertainty, and it's certainly clear that there is no reason to model the uncertainty in a similar way. So the way the uncertainty parameter, which is the growth of the demand from now to 20 years into the future, this has a particular behavior which is very different than the behavior of the uncertainty of the, let's say, wind speed over here in this particular campus every day. Okay? Yes, please.
Okay, I think Maradona and Alan have the same question as mine. So why not the other way around, to model the long-term uncertainty by stochastic programming and the short-term by robust? Because we can say that, well, the future, the short-term uncertainty is hard to predict now. We don't know what will happen. So by uncertainty set, it's easier to characterize the uncertainty. So let's go for a robust optimization for short-term. For long-term, we really don't know. Okay, let's produce a few scenarios and treat it as a stochastic variable.
No, I think it's perfectly valid what you say. So no, perhaps the only additional observation, I think it will be good to do maybe to compare one thing versus the other. And the only thing is that to emphasize, I think emphasizing robustness is particularly relevant in long-term decisions. I want to be robust in long-term decisions, but of course you can do that with the stochastic programming as well, because you can use a risk measure or whatever to do that. And so anyway, the motivation for this in this particular example is basically, well, robustness is important in long-term decision, because in short-term decision, if you do something wrong, it doesn't matter. You fix it in a day. So if I'm selling in a market and I lose a lot of money, one day I cannot lose so much money that I get bankrupt. If I make a wrong decision in the long term and I actually build a plan and there is no future for this plan, then I'm bankrupt. That's the point. So but I think this is not in contradiction what you say. Just we want to emphasize that long-term decisions should be robust. And if we can do that either with stochastic parameter or robust optimization. I think this is fine. Yeah, good observation. Okay, so this is what we are doing here. So let's do an example and then we'll do a short break. So let's just go to the example. You have this is the slides. They're pretty informative, I believe, so that you can read it then and get the information. This is why I'm jumping pretty much. So let's say that we have an example over here. We have the options to, we have a very expensive generator over here. This is DTU, for instance. We have demand in DTU is a random variable, is 3 or 5. And then the production cost of this generator is 10. And we have the option to build over here wind generator, either of capacity 2 or 4, okay? And the energy cost of this wind generator is going to be 0. This is not true in general. Let's assume that this is 0, and the building cost, the power cost is 1, okay? And then whatever this Wing machine is going to operate always under two scenarios, either 3/4 of the capacity or 1/4 of the capacity, with probability 1/2. Why? Well, I simplify things. So I'm saying if I build X, it's gonna work only in two possible ways, either 3/4 of X or 1/4 of X. That's the way it is. So let's build a stochastic programming in this case. So over here, again, we have the option to build either the capacity of this machine is going to be either 2 or 4 over here. The long-term uncertainty is going to be the actual demand. You can look at that like the demand in the one whole year. Either is high demand or low demand, whatever it is. I'm very simplifying this case. So this is the long-term uncertainty is either 3 or 5. And then either if I build 2 or if I build 4, okay, I have two scenarios, so I'm going to embed the two scenarios within the operating condition. I'm using the superscript 1 for scenario 1, superscript 2 for scenario 2. So it's actually a scenario 1 happen, means that the actual production of the wing machine is going to be 3/4x. So the production of the expensive machine, this is scenario 1. So the production of the expensive machine of scenario 1 plus the actual production of the wing that I built. And I don't know if I'm gonna build 2 or 4 over here. This is gonna be equal to demand, which is the long-term uncertainty over here. Yeah.
What is the short-term uncertainty?
Is this probability? I say that the wing is gonna be this or this, and everyone has a probability of 1/2. So they have two scenarios, right? This one over here and this one over here. Okay, so this is the, for first scenario, this is the first scenario. So I am embedding a scenario description for the short-term uncertainty, and I'm using some kind of a robust view for the, with respect to the actual demand over here. Okay, so again, this is the, this is, well, we can produce, we do the enumeration over here, and perhaps some observation. These models are not, they're not different than the adaptive robust optimization models. Simply, we are making more complicated the operational problem. What we are saying is that, well, when we build something, and the uncertainty, the long-term uncertainty realizing a particular way, I not only have one way to operate the system, I have many ways to operate the system. So let's consider the many ways to operate the system, not just the one way to operate the system with different scenarios. In that sense, we are doing things more realistic in that sense, I believe. I'm briefly describing adaptive distributionally robust optimization is something that relates with adaptive robust optimization, not with the previous one, not with adaptive robust stochastic optimization, okay? It's a way to try to sophisticate the description of the uncertainty set, okay? And I think there is a particular interest by the mathematical community or the OR community with emphasis on mathematics because this has a very nice properties in some sense, okay? And it's a nice way to expand the description of the robust set, okay? So let's go a little bit over here. So what we say again, we have the decision over here on the X, and then let's say, well, over here we know that we have uncertainty variable, or that we are not going to say that this belongs to a set, because we will say later on what we describe the robust set. This is kind of a strong assumption. I'm saying this variable, for instance, a very simple set, that the one that we are going to use is bound. So this variable, I don't know what is the actual value it's going to be in 20 years, but this is going to be between 1 and 10. Has to be between 1 and 10. as an easy way to describe. So can we do something more sophisticated than that? And this idea over here, I say, well, let's say that I don't know which is going to be the distribution of the, think about just a single random variable, a single demand. I don't know what is going to be the distribution of this random variable, but I want to characterize, to relate the distribution of this random variable to historical data, to historical values. So I may have historical data of this random variable, so I can build an experimental distribution function, and I want to say, well, I want the description over here not to deviate too much of this distribution. It might deviate, and I want to make the decision, again, in the more protective way, but assuming that the distribution of the random variable that I'm describing here is not deviating that much from the original distribution. This is a way to look at that. We can look at that in many different ways, okay? So it's an attempt to try to sophisticate the description of the uncertainty set. This is what we do over here. This also related to combines something in between stochastic programming and robust optimization. So this is why a lot of the people in the stochastic programming community has been attracted by this kind of ideas. Okay, so so this is what we do. And again, since we have a distribution function over here, then we need a measure to describe the objective function. But this is not related with, let's say, with the decision that we make at the last stage, but with the decision related with the uncertainty with the random variable that we have over here, okay? So this is an expectation, might be something else, like another measure, like C-bar or whatever. So, okay, and the structure is pretty much the same that we have been describing. So let's go to probably an example over here. So in this case, this is just a particular example. We can do different things, but just as an example, this is the long-term decision, the planning decision, as we have been doing all the time. And then I'm going to describe the distribution of the function by scenarios. And I'm going to use a number of weight for the scenarios, in this case, sigma 1 to sigma n. Since they are describing the different scenarios, they have to add to 1. And then I'm going to say this weight of the different scenarios that I have, they should not deviate significantly from this hat that I have over here, which is the particular weight that I identify from the historical data, from the empirical data that I have related with the distribution, okay? So what I'm saying is very simple. I'm gonna have a number of scenarios, but the weight of those scenarios, I'm gonna allow them to not to be exactly the one that we have from historical data, but I allow them to deviate because it's a way to describe the uncertainty. I mean, history is not everything, so the future may be different. So I allow this weight that describes the distribution. In this particular case, I have a number of scenarios. The scenarios are fixed. The weight are the extra component to describe the distribution. I allow this weight to be different. So this is the variable that I have in this particular case. And over here, I have the objective function related with the description of the scenarios. And of course, I have constraint for every particular scenario. So those problems are, in that sense, are exhaustive as the stochastic programming problems are, because I have to describe all the scenarios, all the relevant scenarios over here. Okay, so that's the basic structure of this problem. Let's do an example. Let's do the same example that we have previously over here. We have an expensive generator over here supplying this demand over here. And then I have a very cheap generator over here. I want to decide which kind of transmission line should I build here, either capacity 2 or capacity 4. So I should be able to move 4 or 2 from this one over here. And the per unit building cost of this line is actually 1. And then we are going to assume that the historical information that we have is that we say that the demand, in this case, the demand is located at node 2 and is described by data-derived distribution that include 2 demand values, 3 with probability 1/2, and 5 with probability 1/2. So now is the demand over here, and they say, well, from the history, I can say that the demand is either 3, this is either 3 with probability 1/2, or either 5 with probability 1/2. And I'm gonna allow my model to change these probabilities, not to say this 1/2, this 1/2, but to change the probability, not deviating a lot from this 1/2 and 1/2, not a lot, just a bit, what I consider reasonable. The farther I allow the deviation from here, the farther I'm moving from history. And this is the way I describe the uncertainty in this particular case, okay? So let's look at this problem in this case. So I have 2 scenarios. The weight of the scenarios are not 1/2 and 1/2. They are gamma 1 and gamma 2, whatever they are. They should not be very far away from 1/2, but I allow them to move in order that I do not rely completely on history. Relying completely on history sometimes is not a good idea. When we do predictions, we rely on history, and often we do bad predictions doing that, right? So this is what we want to do here. So we have to wait for the scenarios, this sigma 1 and sigma 1 and sigma 2. They have to add to 1, and then I say that the deviation absolute value of this one and absolute value of that, both together should be below 0.1. So just an example. Okay, so I'm just weighting the scenarios in a different way. And this is the way I represented uncertainty. With respect to the original scenarios that I have from historical data, that they were 1/2 and 1/2. This is the hat that we were using later. Okay, so, and of course, since we have 2 scenarios, this is the cost associated with the first scenario, this is the investment cost, this is the cost associated with the second scenarios, and then over here we have the condition for the first scenario, the condition for the second scenario. Okay, so we can do that. In this case, what I'm saying is, well, the scenario description with the probability of every scenario that I have from historical data, I don't want to deviate much from that, but I allow some deviation in order to describe further the uncertainty. I can do things like look at the moment. We can look at the moment of a distribution and say, well, I want that my new distribution, the first moment, the second moment, the third moment, not to be very different with respect to the moment of the original distribution, or the historical data that I have. Can do things like that as well, and make life complicated as well in doing so. Okay, so an important thing here always is important that when you use a technique, look for a justification for this technique. You don't use a technique because, I mean, everybody's using this technique and this is in fashion. No. Look, is this make sense for the problem? Is this reasonable? Are we getting close to the reality? Be critical to everyone. First of all, with your PhD student. This is, I think that was my first observation to all my students and to Jalal, that he actually, in the old time, he applied this, he actually followed this advice, which is you should be critical with your supervisor. You should challenge the opinion and the view of your supervisor. The best that you can do that, the best the research advance. And this is, if you're a good PhD student, you should challenge what your supervisor is saying, that for sure. That's a critical point in learning. So be critical to everyone, of course. So anyway, so don't use that technique because there is a lot of people doing that technique. And this is in fashion, for some good reason about that. Well, this is an absolute value. We can get rid of these absolute values, still keep the problem linear. But anyway, this problem is linear. Well, we have bilinear terms over here because gamma is a variable and y is a variable. So we have, again, this objective function, which is bilinear. So this is not linear. So this is complicated. And then sigma 1 and sigma 2, they are continuous. So we cannot solve this problem easily. Okay, I cannot use the enumeration that I have been using previously. So I have to use really the technique that we are going to describe in a while over here. Okay? So even though all this is linear, but this is continuous, so this is bilinear, so not easy way to deal with that right now. So, okay. 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 So perhaps a final observation is that this type of model are not very different from the adaptive robust model. So mathematically, they are not much difference. They have a stochastic programming description, which means you have to be careful with the number of scenarios with the description that you do. Otherwise, you may easily get into 10 to the 10 variables, 10 to the 10 constraints, which is a complicated thing to do, right? But anyway, so that's another thing. And let me talk a little bit about robust set in, again, introductory, simple way. And I will mention a little bit things that you should do to make this more complicated, but just to describe them. So the more typical robust set that is used, commonly they are boxes. This is a box, right? So I have a reference value, the forecast. I use all my ability to forecast the actual demand in 20 years. And I said the forecast is going to be 83.25. So this is the reference value. And I said, well, but it can be a little bit low and a little bit above. So I use a box for this particular value. This particular case, in this case, will be, for instance, the peak demand in a particular node. And we have peak demand in different nodes of the system, so this will be spatially located in different areas. We're looking for a power system. I think the demand in a particular area, because people decide to move over there, is grow pretty much, but in other places, a rural area, I don't know, maybe not that interested, so the peak demand there is going to be different. So we have a spatial, in the case of power system application, we have a spatial component here. So this box, apply I, will be the particular node in this particular thing. And so we call this a box. And and again, we have a complicated power system with boxes like that all over the place. Which is the worst situation if we do something a little bit more clever that say, well, the worst is the demand maximum everywhere. But probably it's not a good idea to see the demand maximum everywhere. So we have to somehow qualify that in the same way that we qualify a hurricane. Well, a hurricane so big that everything gets destroyed, then there is no interest of doing further analysis, right? But I can say, well, which is the worst case in which I lose, let's say, 25% of the system? This is the kind of thing. So this is what we are going to do with that. So this is the structure of a box that we often is used in this case. One important thing, these boxes depend on what we are describing. Let's say that we are describing robust optimization for long-term type of analysis, like wind power production from today to tomorrow. It's clear that there's a significant correlation between what happened today and the next hour, even what happened today and next day. So if we're having a windy season, if we have the wind in a particular range of levels in this particular hour, next hour is very likely to be the same thing, okay? And next day is going to be likely to be the same thing. So I have to be careful with these boxes. They cannot be independent. Because if I make them independent, I start doing things as crazy as the following thing. The worst things for whatever thing is one particular hour at minimum, a particular hour at maximum. Depending on the arrangement, you can do crazy things of this type. So you may end up producing set that they are not correlated, they are not linked, in which you are saying that we are producing major changes. Okay. For instance, if we have a unit commitment inside, the way you arrange these boxes may force particular units to start up and shut down. And since you're working for the worst in terms of cost, you may be shutting down a startup unit in app just to satisfy the worst condition over this type of boxes. And those boxes, indeed, they are correlated. So the way you produce those boxes with proper correlation is a very complicated problem. I think it's not easy to look at that. And there is some theoretical kind of dark type of analysis, very kind of complicated, not very intuitive in that line. That I think there is, if you're interested particularly in a statistic, I think producing a description of the correlation of a set that describe the evolution over time of particular quantities like wind production or solar production is an interesting thing. Okay, so robust set, if we apply that carefully, we have to be careful with that. Of course, we can say very simple correlation things. Well, let's say that the wind interval now, the wind interval in this hour and the next hour is related. Well, at least they deviate 20%. Why? So if you look at the literature, you will see a lot of assumption of this type. And you say, okay, well, do a very thorough statistical analysis and show me why it is like that. And then don't say such things because, I mean, this doesn't make sense. So we have to be careful in this respect as well. And this is an important problem, I believe, because it has a significant impact on the outcome of the problem. So we have to look at that carefully. It's not something that we should ignore and say at the end, well, let's say that they are related, at least they change 20% 1 hour to the next hour. We have to be careful with that because I think the solution is related to that. Okay, so, well, let me go to the uncertainty budget, which is the question that you kindly asked me. Is basically what we are doing here is that the robust set that we have, they're boxes, so and we have n variables. Okay, and we are saying is that this is the particular variable, this is the reference value. Go a little bit to the, maybe we have it in the next one. I have it, no, sorry. So this is the box, So we have the reference value, we can go down from the reference value and go up from the reference value. We have n of them, so this is I, we have n of them. So what I'm saying is that if we add the deviation of all of them and we normalize them, okay, this should be below a value gamma over here, what we call the uncertainty budget, okay? So now the way we have defined that, you can see this can go from 0 if all of them are at the reference value, then it's 0. If all of them deviate from the reference value, then it goes to n. Okay? What we are saying here is that either no one move from the forecast value, from the reference value, or we allow for some of them to move. In the extreme cases, we allow all of them to move. And then if we allow all of them to move, then all the demand, if this is demand, go to the maximum, which is the worst condition. But it's very unlikely this to happen. Okay? So what we are doing is we allow some of them to deviate, and as this change from 0 to n, it's giving us how many can deviate. And the problem select the worst one, the one that deviating make the worst for the problem. And this is what we want. We want to be protected against this situation, which is may happen. Okay? So let's do an example over here. So let's say that we have just 2 of those variables, so we can move from 0 to 2. The uncertainty budget, the reference value is 4. So it can go down 1, up to 3, down to 3, or it can go up 1, up to 5. 4 plus 1, 5 over here. Okay? And the same thing, the reference value for the second one is 6. So it can go down to 5, 6 minus 1, and up to 7, 6 plus 1. Okay? So the budget of uncertainty in this case, since we have 2 of them, so I add together the first one and the second one. Okay, since the step is just 1, this is 1 and this is 1, this is why I just divided by 1 and divided by 1. And then if this is 1, it's only one of them that I allow to go to the maximum. this means, well, okay, one stay in the forecast value, the other one go to the worst situation. This is what we are doing. Which one, whatever is worse for the system, depending on the problem in particular. In this case, probably is this one, but it depends on the particular case, right? This is for one. If we allow for two, then both of them, this is maximum uncertainty, all of them go to the maximum, right? And then if we allow zero, then I say they stay at the forecast value. So the only way for this to happen is that this has to be actually 4 and this has to be 6. Means that we are not moving for the forecast value, okay? So we are planning, in this case, for the forecast. If we go to the back one, which is 2, we are planning for the worst case, because we allow everything to go to the maximum one. And if we go to this situation of 1 in which one of them is the one which is going to be at the meeting. So this is the concept. This is the concept. Very simple. We can make this more complicated, produce these boxes more linked together, but at the end of the day, we are doing things like that. Okay? One other interesting thing that we can do is, well, not yet. You can see we can produce here a sign of, we can use this U and U2, we can all type of algebraic relationship between them. So instead of doing things as simple as this one, we can relate them in a different way if we want. That it may make sense from the, depending on the problem that we are doing, but the way I'm relating this way, I can do something else, is what I'm saying. Not just being very precise, but I can link together algebraically in a different way, in such a way that I limit the uncertainty in that way. Okay, so that is the way we can correlate them. Let's say they cannot move, they have to move together up or go down together. I can say things like that as well. Okay. Okay. Well, some observation of why robust optimization. Well, I have been doing stochastic programming for maybe 20 years. And then, and you know, the stochastic, well, now there's a lot of people moving in the two communities. When the old time, around 2004, 2005, they were two communities fighting each other, so they didn't like each other. So you go to the technical conference like Inforce or Euro, and you can see the robust optimization people not talking with the stochastic programming people, and they don't know what they are doing. They are doing bad thing. They don't understand this, and so on. So now there is a lot of more community, but still there is some sense of this kind of things over there. And so what this happened is always a good idea to why we are doing a particular type of modeling, right? And again, I think robust optimization we discussed it, is a good way to emphasize when you have to make decisions which are important in the sense that changing those decisions is complicated. Again, if you have an uncertainty like the market, electricity market tomorrow, if I offer in the market, I may lose money, but I cannot use so much money that I get bankrupt. But if I make the decision of building a particular power plant, which is a huge amount of money involved from that, if I make the wrong decision, then I'm in trouble. So anyway, robust optimization is not the only tool for that, but is naturally fitted for this kind of thinking, right? And this is why, this is one of the reasons, is what I say here, is this what it means over here. Another interesting reason is, of course, we can control the level of uncertainty using budget of uncertainty. We can sophisticate those budgets of uncertainty. So we have a mechanism to control the risk. This is not different from stochastic programming, because in stochastic programming we can use a risk measure like C-bar or whatever and use this technique to actually tailor the level of risk aversion that we want to incorporate into the model. This is not different, but in this case, perhaps it's done in a very particular, simple way. If you implement a very large problem with a risk measure like CVAR, those problems tend to be, let me be precise here, computationally delicate. You have to be careful. You cannot say, well, Gurobi is great, I just inject Gurobi and get the solution. No. Well, a particular decomposition technique, I use Bender. Bender is great, it usually works very nicely. I inject Bender and work. No. You may get surprised, so I think it gets a lot of careful implementation of the technique that you are using for the actual problem to work properly. So it's complicated to implement that in a very effective way. Particularly, you use decomposition technique. Okay, so and I believe robust optimization is a little bit more robust in that sense. So it generally gives you less trouble at the time of actual practical implementation for large problems. Okay. And finally, with robust optimization, we get some kind of complication in the structure of the problem. We may get, if we are not careful, we can get nonlinearities. We can get bilinear terms, product of variables. We have to be careful, and this entails some complication. But anyway, we get rid of scenarios. There's no scenarios in robust optimization, at least in this standard adaptive robust optimization. We may use scenarios for something else, and then we have the trouble of the scenarios. But anyway, the problem with the stochastic programming, as all of you know, is that if we have a multi-state type of problem, we need a significant number of scenarios, and it's pretty easily we get computational intractability. I mean, getting 10 to the 10 type of variable, 10 to the 10 type of constraint is not complicated to do that in a careful description of the models in this type. If we have this size of problem and binary variables, we are in trouble. Okay? Unless you are, well, anyway, chemical engineers, they produce very interesting algorithms. But of course, you are not, for not being in trouble in such situation, you have to use decomposition and decompose the problem massively. Okay? And that is an extra source of complication. Okay? So, okay. So that's okay, and that's it. We are, well, let's move now to, unless you have any question, this is my introduction, so to speak. I'm going to spend some time looking at the algorithms. Yes.
My question is different. If you compare stochastic optimization and robust optimization, both of them are very much dependent how accurate these scenario sets are generated. Mm-hmm. Like how accurate is the like a parameter, uncertain parameter is forecasted, and then scenarios are generated. But they will compare at the end solution. Which one is more sensitive towards accuracy? The
yes.
estimation of this parameter, like
I think it's pretty much depending on the type of application that you do, but I think if you do a careful implementation of both technique and assume some kind of particular behavior of the stochastic variables, so let's say that you assume the stochastic variables are normally distributed, would allow you to describe, the scenarios in a very exhaustive and precise way, and you consistently build robust set based on this assumption, you can actually prove that both of them work in a very similar way. There is very interesting work of Professor Bersimas actually doing that. And yes, so if you use, let's say, implementation of stochastic programming with CVAR, to control the level of risk, and you use a budget of uncertainty like that one, and you carefully do the two things, you get the same result for both of them. The range is different, so you don't know exactly, but for some, you're installing a lot of things. If you have a lot of risk, and describing this risk either by the uncertainty budget or the other thing, and then if you decrease the level of risk, you start building less and less things. Your particular question of how sensitive is one technique versus the other. So if, let's say, moving the uncertainty budget, suddenly I move a little bit uncertainty budget and my first state variable changed dramatically, I think this is very much problem dependent. So I have some problem in which you move the uncertainty budget slowly and the building at the decision on the first stage move slowly, and some other that suddenly you move a little bit the uncertainty budget and dramatically change. And the same things happen with the stochastic programming, with the CBAR. I think this is more problem dependent. So I will say if you have, let's say,
more like stochastic and robust comparison, like accuracy of the solution of any type of model or problem.
Yes.
Which approach is more sensitive towards this accuracy generated or estimated parameter? Since
since you are doing different, I think you are assuming that you are moving the uncertainty description, either the level of uncertainty or the risk parameter that you're using in stochastic programming. I think if you use one versus the other, you get the same result. If you're carefully doing one thing at the other, you get the same result. And if you move the uncertainty budget, increase the uncertainty budget, you are getting solution. You are getting a variety of solutions for building a lot of things to not building a lot of things. If you do with the stochastic programming the same thing, you get the same type of solution. Okay? And I think they are pretty much the same thing. And what depends on one problem to the other is that the way the first state variable may change very rapidly and very slowly. And this is an important thing because, how sensitive is the actual first state variable with respect to changing a little bit the uncertainty level. So, but I don't see difference. I don't see difference in the two techniques in this case. So if you are carefully implement robust optimization, you carefully implement stochastic programming with a risk metric, and you change the parameter describing the uncertainty level in one and the other, you describe the same type, you get the same type of solution, okay? Something else that I believe is relevant, in any case, if you want to look for the quality of the solution that you are generating at the end versus another type of solution generated by other model, I think that the right way to do is to use out-of-sample simulation. So when you have a solution, you have another solution. Let's say one you got it from stochastic programming, another for robust optimization. They're slightly different. Let's check which one is better. So you just simulate what is going on in the system with this actually investment decision with the other investment decision and see what is better in 20-year simulation. So that's at the end of the day. But I don't think they are very different. So if you implement carefully stochastic programming, you implement carefully robust optimization, you explore all the range of variability of the uncertainty description, you get the same type of solution. It's my experience in the problem, yeah. And in one case with more computational trouble than in the other. I would say generally you have more computational trouble using stochastic programming descriptions.
Still deterministic motion, going to the worst case, but still it's considering one type of scenario, which is the worst case scenario, right? Mm-hmm. And but with stochastic optimization, still we consider several type of scenarios with weighted differently. So if I'm doing a bad job at the beginning with the estimation, maybe with stochastic optimization, still I will be a little bit in a safe mode, not to lose completely everything. But with robust optimization, if I'm doing slightly bad in that first stage, like estimation and then generation, this set and all these things, I think it's more crucial there to be very, very accurate.
Yeah, maybe. But that's the specific problem of what happens if we are unable to estimate in a precise way, of describing a precise way the uncertainty. So which technique is better versus the other if we are not good describing uncertainty, so to speak. That's the idea. Yeah. Maybe you're right. So maybe you're right. When we compare both of them, we did our best to describe the uncertainty in the best possible way that we could in both of them, and also make them consistent, which require that you assume a particular probability distribution and then be consistent with this probability distribution of both of them. Professor Bersima has very nice theoretical work on that. So you can prove Bersimas from MIT. Yeah, I can. I'll show you a picture of him in a while. Yes. So and then he has very interesting theoretical result. And I had been working with chemical engineers actually doing experimental work, and we also got the same type of analysis. Yeah. Okay. So this is the algorithm that we generally use to solve those problems. Was proposed not a long time ago. If you look at the algorithm, we will look at the algorithm and say, well, this doesn't look like a good idea, but we'll see. Well, first of all, I'm not going to do anything. I'm not going to say anything particularly sophisticated about robust set in this particular case. So whatever it is, uncertainty budget, a linear description of linking together the variable of the uncertainty cell. So whatever thing that we have over here, and this is the type of problem that we want to address. I have assumed that the right-hand side problem is linear, okay? We'll say a little bit more about this linear problem. This can be, not necessarily has to be linear, but we should be able to merge this problem, the second level and the third level problem. So which means that we need some convexity property here, and we don't, if we have 0, 1 variables over here, we have to do something else. And I'm not addressing these kind of things right now. Okay, so this problem that we have over here is continuous and has some convexity property. We are in a tutorial. We may try to do, well, but this is a unit commitment. A unit commitment has 0, 1 variable. Well, this is a particular problem in the US, not here, because market here, they are not based on unit commitment. So we can safely say that there is no binary variables here. And this is a description of the market. In the US, you cannot say that, actually, because the problem is the problem that this solves is a unit commitment problem with 0, 1 variable. But anyway, let's assume that this is a continuous problem and has appropriate convexity property. For instance, it's a linear one. We can do things with more complicated settings, but I will just go to the basic, and this is the purpose here. Okay, so this is linear, and you can see the variables of this problem is the y, is y over here. So we have, this is a part of the variable related with this constraint. This, let's say this is the investment cost. Actually, the I relate to investment, and the O related to operation. So this is related with the operation. And when describing the operation of the problem based of equality constraint and inequality constraint, right? So this is the dual variable associated to the equality of the dual variable vector associated with the equality constraint. This is the dual variable vector associated with the inequality constraint. And I'm explicitly recognizing that this matrix A and D and this right-hand side vector B and E, they may depend on the variables of the other problems. It depends on the, if I build new plans, these new plans will gonna affect the way I operate the system. But the building of the plan, the capacity of the plan is a constant from my problem. It's not the Y is the operating variable of the problem, right? So I'm assuming that this A and D, which are two matrices, they depend on the variables of this other problem. Okay, but I'm assuming that this is linear. A very interesting alternative to do that is, if we want to describe the operation of a power system, we can use this look like economic dispatches. Let's forget about the 0, 1 variable. So this is an OPF. So we can use an OPF here, but the OPF is a nonlinear problem, non-convex in general. So we can perhaps relax this problem and produce a second order programming problem, which is a good thing. And then, so this can be a second order, a convex problem, which is a second order programming problem. One observation here, I think some of you are working on relaxation. I think relaxation for the OPF problem, for instance, it might not be a good idea. Let me be kind here, because I mean, if you relax the problem, you get a solution which is infeasible. And if you are solving a problem for the implementation in 5 minutes, you don't want an infeasible problem. So I think a significant part of the work that has been carried out by distinguished people like Professor Lowe that was here presently, and Javad Labaei, I think they're interested not by itself. The relaxation produces an infeasible solution, and an infeasible solution is useless because you cannot implement it. So why you want to produce infeasible solution? And feasibility is an important thing. If you want to implement things, you want feasible solution. If they are optimal, good. If they are not optimal, it's okay. We can live with that. But for implementation, you want a feasible solution. Feasibility is the critical point, okay? If you relax and you get something infeasible, this is useless. Well, let's see. But you can, of course, you can use that for something else, which I believe is the interest of the relaxation. For instance, here, I'm not deciding here, I'm not generating a solution that I have to implement, but I'm using here to decide it over here if I built a line or not. And this description of the system, well, if I have slightly infeasibilities, from the point of view of building something, it's not that important. It's like small infeasibilities are relevant if I have to implement the solution. If I don't have to implement the solution, but I just, well, you know, if we use here a DC optimal power flow, this is fully infeasible. It's unimplementable. You cannot implement what you get. Assuming that the voltages are 1 is crazy. This never happened. If you solve a DC power flow and you get a solution, you just throw away the solution. It's useless. You cannot implement it. So we do that all the time. So I'm complaining not only about the relaxation, but this traditional, let's say the common relaxation that we use, that is the DC OPF. But over here, we are using all the time the DC OPF, not for getting a solution implementable in the system, but to make decision about which kind of things we build. And to make decision on which kind of things we build, if voltage magnitude is relevant, then we should use here not a DC OPF. We have to represent the voltage. And representing the voltage, a good way to do that is a relaxation of the algorithm. Okay? So anyway, maybe you have a different opinion than me, but I think this is an important thing. From the operational point of view, the operator wants a solution that is feasible. This is the first thing. And then if it is optimal, good. If it is not that optimal, well, we can live with that. Okay? So this is important from the operational point of view. Okay? So let's go back to the, yeah.
Sorry, but if you make a decision at the planning stage, it is not feasible in the real-time operation again, it's the same thing, right?
Well, you have a lot of time because it's a planning decision, and then you have the operational decision. You will build a very much accurate model to make sure that the operational decision gives you an optimal solution. In other words, you have time later on to make sure that in operation you get a feasible solution. Of course, the best thing will be you do the super model, including everything with all the details at this level. So let's use here AC OPF with 0-1 variable, which is the reality. This is the way you operate the system. But if you do that, you cannot solve the problem. Okay, so that's the problem. So I have to simplify that. What I'm saying is that simplifying this here, I don't have any option. But in any case, I'm saying it's better to use relaxation that using just a DC linear model. This is what I say, because we are getting close to the reality, and we can do that, because still the problem is convex and we can use it. Of course, the ideal thing will be to have here a full AC with binary variables. You cannot solve that. But anyway, and we can do this approximation because at the end of the day, you have at the operational stage, maybe you have to install a capacitor bank over there to control the voltage because the voltage was not properly represented here, but that's okay. But what I'm saying is that if you're now solving an OPF in 5 minutes to tell the operator, do that, you cannot use a relaxation. It's crazy using a relaxation because you're not getting a feasible solution. That's the point. So, and we have to say that to the relaxation people. That's an important thing.
I'm not intending to defend them, but at least for radial systems, we know that the relaxation is
yes.
good. So also for transmission system or mesh systems, we know that in most of the cases it's rank 1, so it's exact. So of course we cannot promise beforehand for mesh systems that it's exact, but for most of the cases it looks like that it's exact.
Well, yes, of course. I think I like to, let's say, emphasize on being provocative because that's the way I get you wake up with this mathematics here. Things are not that complicated, but anyway, the basic point that we cannot get an infeasible solution. If we need a tool for the operator to implement, we have to make sure that the feasibility is the first criteria, right? Again, I think, of course, for distribution system, but we don't need to solve, let's say, very complicated operational problem. But I mean, the traditional OPF, security constraint OPF, that the operator solves systematically a few minutes before the actual implementation of the actual power delivery, I think this is a critical point, and we cannot risk that the solution that we get is infeasible. This is what I'm saying for this particular thing. But what I'm saying is that all the very valuable relaxation work carried out by very distinguished people is more useful for these kind of things, not for the actual implementation. So we were not able to solve over here to represent the voltage here in a planning problem. In a robust optimization of this type, we can now use here a careful representation of the voltage. If the voltages are important, if they are not important, we don't need to represent them. But let's assume that they are important for whatever reason of the system. And this is happening more and more because the system building, I suppose, in Denmark is impossible to build a transmission line. In most part of the Europe, it's impossible to build a transmission line. Nobody likes a transmission line around there. So everybody will complain about the transmission line. So it's very difficult to build transmission lines, okay? Just as an example, Scandinavia and the continent, the interconnection is about 10%, not more than that, if I remember right. Italy with the rest of Europe, the interconnection is before 10%. The Iberian Peninsula, Spain and Portugal connection through France with the rest of the continent is below 3% of the peak demand in Spain and Portugal, which is below the actual connection between the UK and the continent, so which is a little bit above 3%. So Europe is very disconnected from the electrical point of view. It's very disconnected. Why? Because it's impossible to build lines. That means that voltage became more and more important, and transmission constraint became more and more important. And this is why we may need to be precise over here. In the old time, with a lot of transmission facility, that was not important. And this is really the relevant, I think the relevant contribution of the relaxation is applied here. And this is, Professor Bienstock from Columbia University has been promoting this kind of thinking, and myself, I have been doing that as well, and I think it's important. Anyway, this is a robust optimization problem. We don't need to use a linear programming problem here. We can use a relaxation described more in more precise way what we do. Okay, but let's go back to the algorithms. Okay, so this is linear. So let me write it there. The third level problem is linear like that. So I just thrown away this part, which is constant. This is constant because this belongs to this problem. So this is linear. This is the linear problem here. So this is the dual. So I don't know If you can, I guess your mind changed from primal to dual all the time without thinking. I hope you can do that because this is important and you do these kind of things. But let me quickly go over here. This is the primal. So this B and E appears in the objective function. B is over here, E is over here. And then this matrix is transposed. So we have A and D transpose. And then this is the dual variable lambda mu. So we have lambda mu. And then finally, what we have the objective, the constraint, in the primal, the objective function coefficient is over here, like the right-hand side of the dual problem. Okay, I think this is correct, this dual. You can check. And in this case, these dual variables are free because they are equality constraint, and this is a mean, and this is greater than, this is non-negative. So this is the dual. So now I have the dual. The primal is a mean. The dual is a max. Okay. So I have merged the third level problem and the dual of the third level problem and the second level. So now for me, this U, this is the variable describing the uncertainty, is the variable of the second level problem. Now they are merged together. The objective function is the same. Okay, because it's the whole objective function, excluding the part corresponding to the x, because it's not dependent of this variable. And then we have here the uncertainty description, the uncertainty set description, whatever it is, with all the uncertainty budget and all these things. And then this is the dual constraint that we have built, and this is the dual variable. So this is the second level problem that we have. This is the merging of the second level problem and the dual of the third level problem. Okay. So let's assume that this is the second level problem and third level problem. Okay. Let's assume now that we start with a given value for x. So let's assume that the x is the planning problem, the initial variable, the variables of the first level problem. That's fixed to a given value. And then given this fix to a given value, we can actually solve the dual problem over here. Because if we fix the x, is fixed to this particular value, okay? We can solve this problem. It's just say, well, let's give a try to the actual investment. Let's invest this line, that generator, that thing. We do the planning, long-term planning decision, and then we operate the system, the operator of the system, taking into account this max mean. So consider that I want to operate the system in such a way that the worst happen. This is that we have here, the worst happen in U, and then the best happen from the point of view of the primal. That from the point of view of the dual is the max, is the worst again in lambda mu. So this, we are merging together these two problems. Okay, and then solving this problem, I get the U, the variable of the second level problem, and the lambda mu, which is the dual variables of the third level problem, the corresponding to the operational problem. Okay. So, this, let's assume x equal to this given value. We do that this arbitrarily, and in the so from the point of view of the whole problem, if I fix this arbitrarily, then I may not select the best one. The overall problem is to minimize, okay? And I have already said, let's do this investment. So then arbitrarily fixing this investment, so this might not be the best one. You have found a mistake over there?
No.
Okay. Because I did that recently.
If I'm not wrong, those terms are bilinear, right? Because U is now right of the merged dual problem of the third level.
In this case, this problem, this is a constant from the point of, well, it can be anything, yes. The problem, when we are merging the problem, we don't know, I don't say anything about that. The merged problem typically is bilinear. That was the question. Yes. Yes. I do whatever I can do. Yes. Yeah. So unless you have some kind of assumption over this use, so yeah. So the merge problem can be a problematic problem. It's not exactly. It's not non-linear. It can be anything. And then we have to find out which is the best way to solve this problem. That for sure, yes. Okay. So, just I was elaborating that since we have arbitrarily fixed that to a given value and the overall objective of the problem is to minimize, since this is arbitrarily fixed, the investment is arbitrarily fixed, so what I'm getting out of this problem for this arbitrary thing fixed is a lower bound, is an upper bound. Because I fix arbitrarily the investment decision, so this might not be the best one. So I'm not going to the minimum, as much minimum as I want, but I get somewhere else in the middle, right? So this is an upper bound. So the upper bound is actually the objective function of this problem over here, okay? And I adding over here the part corresponding to the investment that I didn't take it into account for the second and third level problem because it was a constant for that one, okay? So this is an upper bound for this problem. And then out of this problem, I built a very exotic problem. So out of this problem, I'm getting this U over here, okay? And now this is the upper bound. And then I fix this U, and I solve a master problem, a very exotic master problem. I don't know, with that one. This problem is supposed to describe the whole problem. So let's see how this problem describes the whole problem. You can prove that this has nice properties. I will not go into that. But anyway, so these problems look like that. I'm minimizing, I'm fixing this. So this is a constant for this problem. And again, this problem has maybe anything. Can be linear, non-linear. Anyway, we have the x. And then we have this new variable over here, eta, and then we have this variable y's, which are copies of the variable. They're variables. They're variables. They are copies of the operational problem. Okay. So what I'm saying is that instead of the investment decisions, I have over here the cost, and I have over here the two constraint, the quality constraint set, equality and inequality constraint of x. And then, I'm describing the operational problem for a given decision of the U over here. For a given decision of the U over here, I'm describing the operational problem, say, well, let's say that this K, this K is just one. We're making just a copy. So what I'm saying is that for a given U, okay, and using this constraint over here, this is describing from below, we will see the operational cost, because what we have over here is the investment cost and the operational cost. The operational cost is described over here, that's what the part over here. But we are using, in this particular case, I'm using hyperplanes of this type. So what I'm saying is using a hyperplane to describe the operational cost. Let's assume the operational cost is that way. Again, using a variable eta, and I say that I have to be above this hyperplane that I'm building here. So this is what we do here. This is the hyperplane that I'm building, because this is this work like a hyperplane over this eta that I have over here, and I'm reproducing over here all the operational variables of the problem. So what I'm saying is basically is every time that I produce an iteration, I'm creating a copy of all the variables of the operational problem. So I'm taking all the operational variables and making a copy of those operational variables connected to the actual realization of the uncertainty. So you have a new value for the uncertainty, and I bring it a copy of the variable connected to this uncertainty. And if I keep iterating, I keep adding new values for the uncertainty and new copies of variables. All of them are variables. So I'm increasing at every iteration, I'm increasing in the number of variables, as many variables as the variables of the third level problem. Okay? This is what I'm doing here, increasing this over here. As we iterate, we reproduce all the variables. It's like, well, at the master problem, I bring a copy of the operational problem, and I solve the operational problem at the same time with the value of the uncertainty U. For another value of uncertainty U, I bring a copy of the whole problem, and I insert it over here. Okay, you can show that this is exactly equivalent if we keep moving and we produce, let's say, that we produce all the possible values of the u. If it is continuous, this is not the case, but we produce all the values. This corresponds to the master problem. And since this is the cause, we are approximating the cause from below. So we want to be a minimum, but being below. So this is a lower bound. And the lower bound is actually this cost of the investment cost and the description of the uncertainty cost. Well, let's go a little bit over here. So this is called column and constraint generation. At every iteration, all the constraint of the third level problem, I bring it here. So if I do that 20 times, I have 20 times the third level problem reproduced over here with all the variables, 20 times the number of variables. Variables and constraints. So I'm adding the constraint because k is equal to 1 to n, all the constraint, all the variable. So this is why it's called column and constraint generation. So I'm expanding the problem in variables and in constraint. So crazy thing to do, no? Yes?
I'm curious, how does it differ from vendors decomposition?
Well, there is no dual variables here. There's no dual variables. Vendors is called sometimes these primal vendors. So the information that you are transferring from the master problem to the subproblem is just this collection of constraints. But you are not. There is no dual variables. You are not solving. Let's say in vendors you fix the variables, the complicated variables, so to speak, and then you solve the subproblem. From the subproblem, you get sensitivities, dual variables to the subproblem, and based on those dual variables to the subproblem, you build hyperplanes. But here, these hyperplanes that I'm building, they are not based on dual variables. This is not dual variables of the subproblem. They are based on this constraint over here and all the variables. So it's primal information. I'm moving from the subproblem to the master problem primal information. Sometimes this is called primal vendors. Yeah. Yes?
Does it have better readability because the vendor's algorithm tends to computational efficiency of the vendor's algorithm reduces in iterations?
Yes.
Cuts.
So basically, if we talk about vendors, I like vendors. I have been doing vendors for many years. but anyway, we can do a lot of, let's say, clever implementations of vendors to try to, for this particular type of application to work properly. I would say if you generate, let's say, the cut in the, let's say, more primitive way that I was describing, so fix variables of the master problem, solve the subproblem, compute the sensitivity of the objective function of the subproblem with respect to the actual value of the complicated variable coming from the master problem, and based on this sensitivity, transfer and produce a vendor cast in the master problem. You can do things much more sophisticated than that. But you can, doing more sophisticated things, you care about the stability, you don't want to get cut that are all the time the same, because one problem of vendors is that you get all the time the same cut, but it's slightly different. So you are stuck in producing many cuts which are pretty close to each other, and you're not moving to other places. Anyway, there's many ways to improve. But generally, for this type of problem, you can use vendor as well. So why not to use the subproblem and use, the traditional way of vendors, get dual variables, and then with those variables build vendors cut that allow you to reproduce these costs with respect to the other one, okay? If you do that, and the people that proposed this algorithm did that exhaustively, for this type of problem, this is much better. It's very anti-intuitive. If I look at that, say, well, I'm increasing the number of variables. If a student of mine came to me with this algorithm, I will say, you are crazy, don't tell me anything. This doesn't work, okay? Well, it happened that it works. Many things, they are not intuitive in any case. So.
Antonio, I think this works, because, we can use it when we have, for example, binary in the subproblem, so we cannot get dual information. So that's the only choice.
Yes.
As you say, compared to vendors, this is, the master problem is growing significantly.
Right.
So I don't think this is more preferable than Bender's. Bender's works.
Yeah. No, but the problem is that for this particular problem, even if they are linear, benders tend to produce CAD which are problematic in the sense that they tend to be very, exactly, and they are very similar. So, yeah.
Two small questions. Do we have proof of convergence?
Yes. Under some particular circumstances. But you can have, if I remember right, let me, so this is Professor Bersimas, and both of them proposed this algorithm mostly simultaneously. This paper have interesting proof of the convergence. I think you need, for convergence, you need the problem to be, the third level problem to be linear. I think they work, or maybe they even relax. The right-hand side problem, the third level problem has to be convex. And you need also some kind of assumption over the uncertainty set. I think they work on the assumptions that they are boxes. So that the uncertain parameters, they are just uncertainty budgets. Yeah. Under those conditions, they prove convergence in a strict way. Yeah.
Yeah. And is this different, very different than dancing wolf, or almost the same?
Dancing Wolf itself is only for linear programming problem and for a problem itself, so to speak. No, I mean, structurally work not very differently, but I mean, Dancing Wolf is just a linear programming problem, a mechanism to decompose. It's an interesting, yeah, there is some similarities, but I don't, in the sense that you are producing column generation. Dancing Wolf is more like column generation. We are getting additional variable as well. Yes, I think so. Yeah. Okay. Yeah. So, but anyway, this is a little bit more general in that sense. So this is these two. So those algorithms from 2013. So before that, we were not solving this problem efficiently, right? So, and they were produced independently. So Bo, I think this paper is a nice paper and is produced some proof. He has also a number of technical report beyond that. And then they, this is the work of Professor Bersimas and Disan. And this is a very applied problem. This is a unit Koopman problem, actually, that they use for that. And actually, this algorithm is embedded over there in an invisible way. You have to look in very detail the problem to realize that they are using exactly this type of algorithm. And the sub-problem that they use is bilinear, by the way. The sub-problem they are bilinear. And they use a heuristic for the bilinear problem, because if it is bilinear, you don't have many options, right?
Heuristic mean, what kind of heuristic in?
They use, if I remember right, they just fix, it's a bilinear, so product of variable. They fix one variable, they solve for the other, then they fix the other and solve for the variable. And this work in this particular problem, it works well. Well, you restart the problem in many starting point to make sure that you are in the right optimizer. But yeah, I think they use this and heuristic as simple as that one. Okay. Okay, so that's the algorithm. So this is the algorithm that is most effective for this type of problem. And we can expand and extend this algorithm in many respects. I wanted you to have the idea, the basic idea. And of course, there is many, if you look at the literature since 2013, a lot of people have been looking into this in a sophisticated way. So, but this is the idea. And the idea is, at least from the computational point of view, is shocking. So I said, you're making the master problem crazy. So this cannot work. The master problem will get stuck very easily. So, well, it's not the case. So actually, you don't need many iterations for typically converge this type of problems. And that means that the master problem is not that huge in many practical applications. Okay? So any observation? So I'm going to look a little bit more in detail to actual examples. And again, a very stylized and very simplified version of problems. But anyway, there is many applications that we can use. And so I have to, we don't have time to go over everything. I was expecting that, so this is not lack of planning. But anyway, I think, again, if you buy the idea that robust description of the problem is a good framework, if you had to make important decisions, decision that the consequences of that decision last, then those are a number of problems. I mean, long-term planning problem or shorter or medium-term type problem are more attractive for the framework, because shorter problems, you can, if you make a mistake, you correct it. You can correct it very easily, but medium-term and long-term problem is difficult to correct. Again, you can use stochastic programming in that sense as well, but anyway. So important problems that we may want to look at them. All maintenance problems. Maintenance are important problems nowadays, and I think there are many challenges related to maintenance problems. So let me describe some of them that may be interesting to some of you. In the old times, well, what did you do with the maintenance of your bicycle? I hope you have a bicycle. Every springtime during the summer, maybe you don't use your bicycle that much, you use the bus. But during the springtime, you just go and I mean, either yourself but you take the bicycle elsewhere. So they do a checkup on the bicycle, so the bicycle will be ready for the summer season, right? So most of the traditional maintenance scheduling problem is related to the fact that, well, let's do on a periodical basis, you take your car every 6 months to the repair shop so they can check your car, if this is the case. So most of the time for the electrical system, power plants are basically maintained one a year. It takes 3 months, basically, 1 month, about 3-4 weeks to actually perform the maintenance of for a traditional thermal unit. So one important thing over here is that we are getting more and more data. So I'm not a fan of I'm not fascinated person with this big data stuff and the cool guys doing big data stuff. But it's true that over here for preventive maintenance, we have kind of big data. If you look at the information that you extract from a combined cycle gas turbine is gigantic. So all the thermal and vibration and all the sensors that have in one of those machines, this is a huge amount of information. It's sampled at very high speed. So every second you have a huge amount of data related with the temperature and the vibration, just to mention two particular aspects of the different section of the machine. And this can be actually transferred to the control center. And so we have a huge amount of information related with the actual performance of the equipment. The same thing with windmills, and you have a lot of information related with the mechanical, electrical, electronic equipment which is over there. Can we use this information to do a clever decision related with maintenance? In other words, if the machine is working great and I don't see anything particularly problematic in the data that I'm getting, well, let's forget about maintenance. Keep the machine working. It's okay. There's no problem. I'm measuring everything and it's okay. Why to stop it every 6 months necessarily to do maintenance? So the point here is of the idea over here. I'm not addressing that particularly in the model that I do, but from the maintenance point of view, we are getting a lot of additional data, and this additional data may be used using big data technique to try to estimate the life of the machine for the future. and then to incorporate that in our maintenance scheduling plan. Okay, this is an important problem, and I think the connect, let's say, all the ideas that are now popping up related with big data, with our particular application with power system. Okay, so again, if you have very good, reliable data on time of the performance of your machine, so use that data to make sure if you want actually to make maintenance or not. And second thing, in the old times, most of the models, if you look in the literature, the maintenance cost is basically independent of the operation pattern of the machine. So your car, you take your car every 6 months to the repair shop, and they check up your car, and you pay about the same because they change the oil, filters, and this kind of thing. So everything pretty much the same, you pay the same thing roughly. Well, there is some machines over here that the maintenance depends dramatically on the operational, let's say, history of the machine. If you have a combined cycle gas turbine, if the regime of this turbine is shutting down, start up, shutting down, start up, shutting down, start up, the maintenance that you have to perform is much more complicated and costs a lot more if the regime of operation of this machine is operating all the time. So we have more and more equipment that the maintenance costs depend on the operation regime of the machine, particularly combined cycle gas turbine. Combined cycle gas turbine, the way you operate the machines, have a dramatic change in the maintenance cost. Okay, this is very interesting because it's a long-term cost that depend of short-term decisions, make the problem very complicated because they are actually collapsing together the long-term decision with the short-term decision. Okay, but anyway, so I think maintenance problems are important. So let's say preventive maintenance. Another medium-term problem is that if you are a producer that use gas, you have to procure this gas. So which is the best way to actually buy the gas to be able to produce electricity? Okay, traditional problem, it will go a little bit up to Norway or Sweden. So which is the way we should actually schedule the hydroelectric system to try to get whatever it is to minimize the cost of operation of the system or whatever. Another thing is that if we are selling electricity, we are a producer, we sell electricity in the market, we can use maybe contract, we can use a shorter type of trading framework like a spot market. So if we use contract and a spot market, which is the best combination of these two things, maybe we can use robust optimization for that. And again, if you're a consumer and you have to buy electricity, did you, I guess, probably produce some of its electricity and buy electricity in a sophisticated way? I suppose it's buy electricity in a different way that you and me actually do. So anyway, this is just typical example of maintenance. So let's do a preventive maintenance problem, a very simple one in this case, but we can just use that framework. So let's say that we have a little bit more sophisticated system now. So we have a generator here, the cost is 2, another one, the cost is 4. We have to supply a load, which is over here, okay? And then we have the injection of this machine is P2, the injection of this machine is P1. We have a capacity of this line, the flow in the line to the load is F1, the flow of this line is F2. We have to supply a load which is 6, and then the capacity of this line is 5, the capacity of this line is 5. So I want to perform maintenance of this line or in this line. And in principle, I want to perform maintenance in the both line. If I perform maintenance, I'm improving the condition of operation of the line, so to speak. I'm going to do over here a very simplistic type of description, but just capturing the idea. What happened basically for the maintenance is as soon as you perform maintenance, the life expectancy of the time to failure of this particular line get much longer. So this is what you do. In this particular case, we are going to do something else. Let's go to the problem. So in this problem, we are going to consider failure of this line. And we describe this by the variable u2, v1 and v2. And we basically say that this line has a partial failure. So it's not a total failure. Is if u1 is equal 1 means that this line has a partial failure that I will describe later on. And similarly, if u2 is equal to 1, then we have a partial failure in this particular line, okay? If I perform maintenance this problem over here, then I increase the, somehow I increase the capability of the lines. I'm gonna do that in a very simplistic way, just to keep the idea. So let's see the way, so these are the variables related with performing maintenance. I have the option of only perform one maintenance, either in one line or in the other, just for simplicity. In terms of uncertainty, I say that the failures may happen just in one line or the other. So it cannot happen in the two at the same time. It happens just in one or the other. Again, a very simplified version to be able to solve this problem. And then the operational problem is over here. So let's look at the operational problem. The operational problem will be the variables are P1 and P2, the production of the two generators, the cheapest one and the more expensive one, and the flow with the lines, okay? So we can see that the flow over here is P1, all the power produced by the generator goes through the load through the line, and the same thing goes over here, so P2 is if equal to F2. Can do that more general in this time, and then the condition that I have is that the flow in this line, okay, has to be 5, which is the reference value, plus 2 times x1. This is if I perform the maintenance of this line. So if I perform the maintenance in line 1, I'm increasing the capacity of this line by 2. So if x1 is equal 1, I say this line, instead of being 5, is 7. Okay. Well, this doesn't make a lot of sense from the electrical point of view. I just wanted to make this from the formulation point of view. And the same thing if this line just suffer a failure, this partial failure means that instead of being able to produce 5, to carry out 5, it's just carry out 1. So it's going to be, we're going to subtract 4 from the actual operation of the line. This is not the reality. I'm not intend to be realistic here. I'm just to show you how we can use robust optimization to model this type of thing. Okay. Over here, this is the limit of this line. This is the limit of the line, and finally we have to supply the demand, which is going to be 6. If we want to be a little bit generic, over here will be all the maintenance will be a multi-machine system, of course, multi-line system. Over here we have all kind of possibility of constraint related with the actual maintenance of the line, including that I cannot maintain simultaneously many lines, and we have a limited amount of people dedicated to maintenance, all this kind of thing, and the cost associated to maintenance, that I'm not considering the cost associated to maintenance, it will be over here as well. Okay, and this cost of maintenance may depend. This is a very complicated problem in that sense. So the cost of maintenance, it may be related to the operational condition. So I have a cost of maintenance relate with this x1, but depend of the actual operation P1. This is make things particularly complicated in that sense. Okay. And then over here, whatever description of the uncertainty, I say, well, the two lines cannot fail at the same time. They cannot, this is arbitrary, so it may happen that, of course, I have to describe the failure of the line maybe with uncertainty, with a budget of uncertainty, okay? And then this is the operation condition. For the operation condition, that will be an optimal power flow, maybe a relaxed optimal power flow, maybe a DC optimal power flow, and in many conditions. This is what we have to do. For, let's say, maintenance take place within 6 months, 1 year. So we have to describe over here the operation of the system for 1 whole year. Okay? This is the kind of thing that we have to do. Okay? Maintenance is tricky as well, in the sense that I cannot, if I'm a given producer, I probably have the right to carry out the maintenance where I don't have the options to carry out the maintenance what I want, because I have to coordinate it with everybody else, because otherwise everybody may want to do the maintenance at the same time, which reduce drastically the reliability of the system. So that means that we need some kind of coordinating mechanism here. The regulator of the system say, well, you can only, during the summer, you can only maintain 2 out of your transmission lines or whatever. So that means that we have a lot of complications here. But anyway, that's a very simple structure of the problem. Again, we describe the uncertainty at the planning level. We decided on, we decided of maintenance policies at the planning level. Then the uncertainty happened, damaging the lines in a particular way, and then we operate the system in this way. Okay, so this is a possibility. We have. Okay, so this is the solution of the problem. Then you have a little bit more general formulation over here, in which you have in the slides over there, in which I describe actually an OPF over here. So let's do another example over here. So let's say you are a gas generator. You have to supply a given demand. A very simplified system in this case, only one generator, only one demand. And this generator has actually to buy the gas either through contract or in the spot market, right? And it has to decide how much gas it wants to buy in the spot, how much gas it wants to buy in the contract to supply the demand over here. And this is the amount of gas from the spot market, this amount of gas from the contract. Again, the spot, it may happen in many time period. The contract happen in for a period of time which include many spot market. So we have a multi-dimensional time framework over here that we have to look at that carefully. So, but in any case, we are simplifying here a single period, a very simple case in this case. So we want to find out which is the contract that I want to buy. And let's assume that the contract, because of the simplicity of the problem, is just 3 and 5. The demand is the uncertainty in this case, can be 2 or 4. It may happen one or the other. And then I operate the system. To operate the system, what I don't buy from the contract, I have to buy from the spot. And the spot price typically is much higher than the contract price. So I want to buy as much as I can. In this particular case, I want to buy as much as I can out of the contract of these two, but I cannot, I should be careful not to buy too much, because otherwise I cannot use it. I mean, okay. So anyway, and again, we want to protect. This is the uncertainty in this case, which is the demand. We have to protect against the realization of this uncertainty. And again, this is the cost. It's 2 times the quantity that I buy from the contract plus 4 the quantity that I buy at the spot market. And then I'm assuming that the conversion gas to electricity is 1/2. So this is the gas, the total gas that I have for the single time period. I multiply by 1/2 because it's the conversion, and then this should be greater than the demand. Pretty simple problem, but again, structurally, we can use this kind of framework to describe this type of model. Again, this will be typically, this is multi-period, so we need a multi-period here versus that. This is a single period over here. We will do that later on. So we have a little bit more general version of this problem later on described. Let's do a higher scheduling, and I think we can finish with that, unless with after looking at that, unless you have any question. Okay. So let's say that again, we want to satisfy the demand over here, and we can do that either using an expensive machine over here that produces Y, or we can use this hydro system, that this is the inflow of water to the system, H. This is the water spill. I mean, if I have a reservoir, I can actually turbine water to produce electricity. We have, this is the conversion from water flow to electricity is this eta that I have over here. And additionally, if the water inflow is this is very high, eventually I have to spill water over the reservoir. So I want to operate the system. Of course, this is a medium-term operation problem. Again, multi-period, we can do things complicated here, but again, making very simple the problem just to clarify the way in which we can use robust optimization in this particular case. So let's go first of all, describe a little bit the water balance. In every hydro system, we need a water balance constraint. The water balance constraint is over here that we have, and we assume that the reservoir over here has to be between 1 and 4. We are considering a single time period. Of course, we should consider many time periods in the real world, but again, a tiny toy model for understanding what is going on. So 2 is the initial content of the reservoir. 2 is the initial one. So H is the inflow. So plus H, which is the inflow, minus X is the quantity that we turbine. And it needed S is the quantity that we spill. S is the quantity that we spill. So this is at the beginning of the period that we are considering, and this is at the end of the period that we are considering. So at the end of the period that we are considering, there has to be between 1 and 4 as well, is what I'm saying. And then I'm saying that this demand, this is water, say water balance and water bounds. Water balance and water bounds. There's no sophisticated water balance because I don't have several time periods, but just one. But this is water balance. And then we have electricity balance, which is basically, I'm assuming this eta to be 1/2. So 1/2 X is the electricity that we produce from the hydro system plus Y, what we produce from this, let's say, gas system has to be equal to the demand. Okay, so the problem looked like that. So I want to find out how much energy I want to turbine. Depending of, I decided to plan for turbining over here. I have two uncertainty variables here. You were asking me as well. In this case, is the demand. I assume that the demands can be 2 or 4, but also the inflow of water to the reservoir. And they are important uncertainty variables in reservoir as well. The inflow, the actual water entering the reservoir, I assume that this 6 or 8. And then Y is the production of this generator that I have. If I plan to use this quantity of water and I need more electricity, for whatever reason, which is generally is not the case, or for whatever reason, I cannot further produce in addition to this X, this may be the allocated production for 1 week. Typically, you solve a long-term type of modeling to allocate water usage per week, and then it's very difficult to actually change the water that you use in a particular week. So let's say that this is the quantity that we are allocated by a particular week. If we don't have enough power, we have used this expensive generator. And then also I say, well, I don't want to spill water. Spill water is wasting everything. So I'm using over here, well, in this case, for this tiny problem to work properly as well, I'm assuming that this is very expensive to spill water. Okay, so this is a penalty for spilling water over here. Okay, and then this is the balance for electricity, and this is the balance for water. And again, this is a kind of framework in which we are protecting, or we are using a robust optimization model for getting, in this case, protection against 2 things: the demand over here that we don't know what it's going to be, and the actual injection of water inflow in the reservoirs. And again, this is a very relevant problem. If we go a little bit up north in Norway and Sweden. Anyway, and we can make this a little bit more generic and interesting. And okay, so I think, let me go back to the beginning. Okay, well, do it, okay. So, so anyway, let me summarize a little bit. I think robust optimization is an interesting technique. It's a complementary way to look to incorporate uncertainty. Complementary to the stochastic programming, the two communities are now getting better together and they collaborating. So I think it will be that will be a good things to see and experience in the future. I think it's important as a general observation to try to understand the problem we try to solve and try to fit the best modeling framework for this particular problem, not the other way around. To say, well, every cool people are doing, I don't know, machine learning, so I should do machine learning, put in machine learning in my problem no matter what. I don't think this is a good idea in general, so try to look at your problem, the physical reality that you are modeling for the good of the company which is paying you, or for the good of the society if a public university like this one is paying you. Try to do your best in understanding the problem and then to try to find the best modeling framework for this problem. And of course, be open and alert of any kind of new technique that may help you to try to solve in a better way a particular problem. And be critical. All the time you use a new technique, a new methodology, try to contrast what you are doing with respect to more traditional approach. Make sure that what you're doing, what you're getting, you can really make sure that this is good with respect to something else. Okay? I think, so that's from the general modeling framework. Again, I think robust optimization emphasize robustness. Robustness is important when you don't want to make mistake. And in that sense, it's a natural way of thinking, not the only one, but a natural way of thinking for decisions that are difficult to change or modify. And I think this is it. What I'm going to do tomorrow, if you are planning to come tomorrow as well, is do something completely different. I have been working for some time on the interaction between gas system and electrical system. And I will emphasize different models that assume that both systems operate independently. If you ask the gas operator and the electrical operator to merge and to operate together the system, they will look at you and say, oh, no way. So anyway, I emphasize models that allow to understand the operation of the system, keeping the independence of both systems. Because I don't think it's realistic nowadays anywhere to try to think of a system which is operated in a merge way, in a compact way. Because I mean, there's different tradition, different culture, different institution. To merge the institution, the tradition, the culture is very complicated. So we will analyze different type of modeling framework from the operational point of view and from the planning point of view of gas and electricity models. And we will use basically the framework of what is an equilibrium. So I will start describing what an equilibrium is from the beginning. You have any question? We have a few minutes. Okay. Thank you. Then I hope I'll see you tomorrow.